Hello everyone, and how is everyone doing today? Today we're going to be diving deeper into the Linux Universal File Model. So in the last presentation I've covered some of the basics of file I/O, opening files, using the different flags for opening files, reading, writing files, and closing files. And as you already know, a file in Linux is basically anything. Even an internet connection is a file, because you can read and write to it and kind of use the same ways of caching the data, regardless of whether it's a file or whether it's a queue or whether it's any other stream of communication. And we're going to dive deeper into this I/O model and cover a little bit more detail how it actually works underneath the top layer, which you usually interact with. So we covered opening files, we covered basic reading and writing, we covered closing files, moving a file position around the file, and brief introduction to IOCTL. And today we're going to be covering a little bit more in detail the atomicity of some system calls. For example, if we want to atomically move the file position in a file and read or write data to that position, we're going to learn how to do that without making two system calls and running the risk of corrupting the data if you have two processes or two threads trying to do the same thing at once. We're also going to be exploring or looking at the kernel data structures which represent files. So we'll look at how file descriptors relate to the internal data structure that contains the file, the pointer, the cursor of the file, and how that in turn relates to the actual inodes that point to the blocks that represent the file on disk. And we're going to be looking at multiple ways of redirecting and duplicating file descriptors. I can see the typo there. It should say redirecting. And we're going to look at performing reads and writes without changing the offset, and also doing reads and writes of scattered data. So for example, if you have multiple buffers or multiple structures that you want to write in a single contiguous block of data into the file, you can actually use specific system calls for that and avoid making multiple system calls. And also you get the benefit of atomicity, that the data is written as a single operation. We're also lastly going to look into using temporary files and basically just creating a temporary file name that is guaranteed to be unique. So let's get started. My name is Martin Schroeder, and I'm embedded system consultant. I build embedded systems, and I help companies develop firmware for Linux, and I also work with RTOS-based systems. So if you have any questions regarding Linux or RTOS-based systems, just contact me. Let's get started. First of all, a little bit about race conditions. So when we talk about atomicity of system calls, basically what it means is that an operation is performed as a single unit. So no other process or no other thread in the same process can interrupt that operation. And it's specifically important when you have files which can be open across which are open globally. So you can have multiple processes pointing to the same file or using the same file, and you can have just one representation of that file being reused across multiple processes. And even if we were using mutexes or other process-specific synchronization mechanisms, we wouldn't be able to guarantee that we wouldn't be able to guarantee the integrity of the data, because we can never be sure if there is another process that wants to access the file, and whether that other process also is going to abide by the rules that we have set up. So for example, if we control both programs, if we have the source code for both programs, we could have a global semaphore that we use to synchronize access to a particular file. But normally we cannot be sure of that. We can have any program accessing the file. We want to have ability to guarantee that certain operations, like for example appending at the end of file, are not being interrupted mid-operation. So we don't want to have two processes seek to the end of file, and then one of them writing some data, and then another one overwriting that data. That would create a data corruption. So that's why we have system calls in Linux that are atomic, which guarantee that no other process can interrupt a particular set of operations. And we will see further in this presentation, we can have multiple operations. You can do the same task with separate operations, but then you can have a system call that actually does all of the operations, but does so atomically, so it cannot be interrupted. A race condition is when the result of an operation depends on the order of access to a resource. So just like I explained shortly before here, when you have two processes trying to write to the end of a log file, if you have both of them seek to the end of the file and then both of them try to write it at the end of the file at the same time, the result of that operation is going to depend on whether they have both have seeked to the end of the file and then are writing at the same time, or whether one of them seeks to the end of the file, writes its data, and then another one seeks to the end of the file after that and writes its data. So the result would be different. And that's a typical example of a race condition. Now, system calls guarantee certain operations happen atomically. We can control file operation atomicity with flags passed to open, and we can also control the atomicity by using specific system calls, which are atomic. So let's look at some examples of atomic behavior which we can achieve with flags that we pass to open. Atomicity one-on-one exclusive file creation. That's one example. So if we call open with a path name and we supply option for creating a file and doing so exclusively, then the kernel will guarantee that all steps complete within without being interrupted in the middle. So there are multiple steps involved when we want to create a file exclusively. And first of all, actually there are two steps. So the first step is that you have to actually check that the file exists. And the second step is that you actually create the file. Now, if we do that as two separate calls, we can actually end up with two processes checking that the file exists and finding that it doesn't exist. And then we can have one process create the file and another process create the file. Now, the second process that tries to create the file, unless that process uses the exclusive flag, it's not going to get any error indicating that the file wasn't, that the file already existed before the process tried to create it. So essentially we end up with succeeding with that operation, but we cannot be sure that we created the file. And that creates a problem if we want to use the file as a log file, as a way of guaranteeing that we only have one instance of a program running. And if we don't use the exclusive flag, then we can have two instances of the program running, and they won't be able to use the file to check that. So that's why we use exclusive, and that operation guarantees that the check for the existence of the file and the actual creation of the file happen atomically. And if we use that, we can guarantee that our logic is reliable. Second example is the appending at the end of file. So normally we would do two steps. We would seek to the end of file, and we would then write data at the end of file. And this works really well if we only have one program trying to do that. If we have multiple processes trying to do that, or multiple threads trying to do the same thing, we cannot easily guarantee the integrity of the data, especially if we have multiple processes. Then we don't have any way of guaranteeing that there is integrity of data at the end of the sequence. So with append, the kernel guarantees atomicity of this operation. So it will always seek to the end of file, and every single write that you do to that file, which has that option, append, is going to do this. It's going to seek to the end of the file and then write data to it. So if we have the specific case of wanting to append at the end of the file, we must use append in order to get atomicity of this operation. And the support of this operation depends on the file system. It's something I mentioned in the previous presentation, where if you have, for example, a file, an easy way to understand this is if you have a file that you access over SSH and you try to append at the end of the file, you cannot be really like if you have shared storage, right? and you have multiple programs trying to access the same data, you can never really guarantee that you are writing at the end of the file, unless there is specific support for that. So the support in the file system is absolutely essential in order to guarantee atomicity of this operation. The next way that we can control the behavior of file descriptors is using the file control function. So typically we would use this to get flags and set flags. And occasionally, like for example, if we there are multiple ways of opening a file descriptor. So for example, if you have a socket, you would use the socket function to open the file descriptor that points to the socket. And even though that file descriptor still behaves like a file, you haven't used the open call to open that file descriptor. And if you need to set any options on that file descriptor, then you need to use file descriptor control function in order to set those options. And this function allows you to set the options afterwards, after you have opened the file. We can have multiple descriptors that refer to the same file. So we can have a descriptor, as you remember, is an integer. It's you're always guaranteed to have the lowest integer used. So when you call open, you always get the lowest possible integer. So it starts at 3. 0, 1, and 2 are the descriptors that are always present. It's the std in, std out, and std error. The standard input, output, and the standard error output. And after that, you would get the lowest file descriptor that is available when you open a new file in the process. And you can have multiple descriptors. They can refer to the same file essentially. And but first they refer to the open file table. So in the there's a global open file table to which the descriptor is pointing. So essentially, when you use this integer number, you are passing this integer number, and then that integer number is converted to the file to the open file structure, the data structure that contains the properties of that open file. And that data structure in turn then points to another structure called the inode. The inodes are essentially the file system structure that represents blocks. It points to the actual blocks that contain the file data. You can have multiple open files that are pointed to the same inode. So you can, for example, open the file multiple times. And when you do that, you can have multiple, you can be pointed to different positions in the file, and you can read and write data in multiple positions of the file at the same time. We have also, so each process has a table mapping of descriptors, and in this table mapping of descriptors to open files, we have basic flags that control the file descriptor. So for example, if you have close on exec, what that means is that the file descriptor is going to be closed. The file descriptor itself is going to be closed when you execute another process. Like for example, if you what happens in Linux is that you first copy yourself as your process, your program gets copied using fork, and then you call exec, which replaces the program that your process is running. And when that happens, the default is that the file descriptors that have been open previously, they are still open. So you can still access the same file descriptors. And this is why when you call exec, you can still write to the same std out as the process that has executed the new program. So if we want to specifically make sure that file descriptors are closed before our new program is loaded into the old process, then we specify close exec option on the file descriptor itself. Now note this is not going to close the file as a file in the open files structure. It's just going to close the descriptor. It's just going to make sure that the descriptor is no longer accessible by the process that is using the descriptor. So you won't be able to, let's say you previously opened the file as a descriptor number 3, and then you called exec, and your current program was replaced by a new program from disk, and you won't be able to access the descriptor number 3 from that program anymore. But the file can still be open. It doesn't mean that the file is completely closed. It can still be opened by another program, still using another descriptor to point to the same open file. The system-wide file table then contains the open file structure contains the cursor of the file, which is where you read or write the current position of the file.
where you read or write data, and that structure also references to an inode. So then we move on to, so let's talk about properties of file descriptors. Now, we know that we can have multiple file descriptors referring to the same open file, and we can duplicate file descriptors. Now, we can actually say that we want to copy a file descriptor to another number, and because there are certain functions, like for example, when we do a printf in application, that will always write to the file descriptor number 1, which is the standard output. We can actually duplicate file descriptors to replace the standard output. So this is exactly like how you pipe a standard error to standard output. For example, in Bash, you can specify that you want to redirect standard error to standard output. And that is done by the duplication system call. The dup2 is the most flexible way of doing it, but there are multiple ways of doing it. Now, the file descriptors can reside in multiple processes. They can point to the same file. They share the same file offset and flags that are passed to open. So if they're pointing to the same file open file structure, they are going to share the same. Basically, the flags are stored in that open file structure, and so the file descriptors are just pointers to the same open file structure. And so you're not, when you do a dup2, you're not actually opening a new file. You're just duplicating the descriptor. That's important to remember, that you're not actually, for example, if you duplicate a descriptor and you seek in using the old descriptor, then you're going to have the same position available through the new descriptor as well. So they are pointing, the cursor is going to be advanced in the global structure. So the second descriptor will see exactly the new cursor, the updated position of the file. We can redirect IO. We can the easiest way of duplicating a file descriptor is basically just calling dup, and dup just duplicates the old file descriptor and allocates a new lowest file descriptor. So, for example, you can see things like close the std error, which is descriptor number 2, and then you can see like dup std out, and that will return 2 because you're guaranteed to get the lowest file descriptor. So unless some other thread in the same process has opened another file, you will get the same. You will get number 2 returned by dup. Now, it's important to see the issue here is that if you have another thread that opens another file, you will have a race condition here. So it's a dangerous way of trying to replace std error. What you need to do instead is use the atomic version of this function, and also a function that is more flexible, where you can actually specify the new file descriptor, which is the dup2. And the new file descriptor is going to be opened at, so the old file descriptor is going to be copied to the descriptor with the number new fd, and if they are the same, it's going to return an error. And it's actually going to close the new FD if it's already open. So you don't need to close std error like we did up there in the beginning. You just need to specify std error, and you will duplicate std. You can essentially duplicate std out to std error if that's what you want to do. Closing, let's see, we have closing on duplication or atomic in this case. We have, on success, we get the new descriptor returned by the dup2 function. So we can just use that new descriptor for reading and writing to the new duplicated descriptor. We can also, there's a third way of doing it, and it's using the file control function, where we call it with the old descriptor, and we specify the fdupfd function, and we then specify a starting point of the new descriptor. So we can essentially set like an integer number where the new descriptor is going to be placed, and it's going to pick the lowest open descriptor that is available after that number. But there's more. There's more. There is. Wait, this is going to be fourth way. Actually, I wrote there was a third way. So it's 1, 2, 3, and this is the fourth way. This is not the third way. So we have the DUP3, which is the fourth way of duplicating descriptors. And here we can actually specify flags for the new descriptor. And the only flag we can essentially specify there, which is descriptor specific, not file specific, is the cloexec flag for the new descriptor. And this is an atomic way of creating the cloexec descriptor that's going to be closed if we are executing another, if we essentially fork and execute another program. Reading and writing files without modifying file position. So occasionally we want to basically seek to a new position, do a read or a write, and then seek back to the old position. And if we do it manually using the functions that like lseek, read write, and then lseek back, it's not atomic. So another process can essentially, if they have access to the same file descriptor that points to the same open file, they can actually change the position of the file. And if we execute another change in position of the file, we are going to get corrupted data because now the order of operations is not the same anymore. So for that purpose, we have the atomic versions of these functions, which are called pread and prewrite. And these functions take an extra offset at the end, which specifies where we want to read or write. And count is the same as for normal read and write. The only difference is that we have an extra offset there, which specifies where we want to do the read or write. And it's equivalent to the 4 operations that we see below there, that seek to a new position, or first of all, store the old position, and then seek to a new position, read or write, and then seek to the old position back. It's pretty powerful. Linux is very powerful indeed, and it's really, really useful that everything is a file. You can literally use the same functions for any type of input-output, whether it's a file or a stream or a socket, whatever. So next on the list is a way that we can write data that is not placed in the same in a contiguous memory block. So let's say, for example, we're trying to save a different number of structures that maybe have some other data that we don't want to put into the file on disk, and we want to basically pick data from this more complex data structure, and we want to write all of that data as like one item after another on disk, but we want to skip some spaces in between there in the original data. So for this we have the read v and the write v. Basically, the good way to remember is that it's kind of like read vector and write vector. I'm not really sure if that's exactly the original intention with the v at the end, but it kind of makes sense that we are specifying IO vector as a parameter to this function, and we specify the number of items in that vector. Now, each item in the vector is basically a pointer to the data and a size of that data. So it's very similar to read and write, except that now we have a vector of read and write items that we're going to read or write. So when we call read, we are going to be reading a contiguous block of data from the file, but we're going to be placing it into a number of items that don't have to be stored as a single stream of bytes. They can be stored in different places in memory. But we're doing it with the same system call. And the limit, the maximum number of these vector items is specified by querying the sysconfig IOV max parameter. Both functions return the number of bytes read or written. So if you're writing a bunch of different items scattered randomly in memory, the return value is going to be the total number of bytes written to the file. And the same is going to be for the read call. It's going to be the total number of bytes read from the file. There is more. As always, there is more. So let's say we want to do the same thing, but we want to do it as a specific offset in the file, and we want to then seek back to the old position in the file. And for this, we have specific system calls that actually achieve that. And they're called preadv and prewritev, and they work exactly the same way as the pread and prewrite in combination with readv and writev. So instead of reading and writing a continuous stream of bytes, we are reading and writing scattered number of vectors. And the number of vectors that we have in the array is specified by IOV count. We can also truncate files, and as you remember in the previous presentation, I mentioned the fact that Linux supports holes in the file. So we can actually truncate the file to a larger size than what it actually is, and the bytes that are not that haven't currently been written, like for example, if I set the size of the file to like 2 gigabytes, right? Then the data is not actually going to be written to disk, so it's going to be a hole. It's not going to take up disk space. It's only going to start taking up disk space when we start writing to the file. And this explains a curious effect of, for example, when we try to randomly write data to a file, even if we sort of truncate the file or create this big file from the beginning and we start writing data to it, we are not seeing the disk space increase, but rather we see it increase gradually. It doesn't increase when we create the file. Now, if you do the same thing on Windows, at least on the old file systems in Windows, you're going to see that when you truncate a file, you actually have to create the file. So you actually have to have a file filled with zeros from the beginning, and then you write at different places in that file. Which is rather unfortunate. It's really a waste of space when you haven't actually written any data. So it's really nice that you have this concept of holes. So you can have holes in the file where the hole itself doesn't take up any space on disk. We also have the issue though with the offset. So the oft type, which is used to specify the offset in a file, it's actually assigned long. And on 32-bit systems, this is a 32-bit integer. And so since it's signed integer, we can only access files that are slightly bigger than 2 gigabytes. If we want to access files that are bigger, we need to use 64-bit long. And on 64-bit systems, we don't need to worry about this because this is the default size of the signed long. It's 64-bit on 64-bit systems. But if we're running on 32-bit systems, we actually need to compile our application with the file offset bits set to 64. And what this does is essentially it replaces all the calls like open, seek, the whole API used for manipulating file descriptors. It's going to replace them with the 64-bit versions of that API, so that we can then transparently use or read and write long files without having to modify the source code. On Linux, the file descriptors that you have opened as part of your process, they're always available in the dev.fd directory. And this directory is a dynamic directory. It's viewed from the process that is actually viewing it. So if we access it, if we call open on a file that is in this directory, then we open the descriptor that is local to that process. And this gives us really interesting possibilities here, because we can now pass file descriptors as files to any command that reads or writes files. So for example, any command that accepts a path to a file would accept a dev.fd path, and that would point to a descriptor. So we can, for example, do things like if we call wget, and we specify the output file to be the std out, and we specify the URL, we are going to be outputting that the contents of that URL to std out, and then we can call diff, and we can pass the std in at any position in the command, and really just by pointing it to devfd0 and compare it to the old content which we have downloaded previously, and we will get the diff of that URL. This is just an example, but you can kind of see the power of this. You can literally just pass the descriptors anywhere in the command, and when the application opens that descriptor as a file, it's essentially opening the descriptor. So it's going to essentially be pointing to std out or std in this case. And this really simplifies putting together commands in Linux when you want to do a little bit more complex stuff with commands, where you can just you don't need to use xargs or anything like that to replace the to kind of place the std in. Like you don't need to have the command support the dash as an std in replacement. You can just pass the actual file descriptor, and it just works with any command that that opens and does something with a file. Whenever we need temporary files, it's a good idea to have a file that is exclusively created and that is unique. And it's important that it's exclusively created. And for this, we have functions that are a function called make temporary file, mks temp, and it takes a template as an argument, and it actually modifies that template. So you specify template, and it will modify the template and give you a file name updated in the template. So that template needs to be a modifiable version of the a modifiable string that this function can modify. And we can also create a temporary file using the temp file function, which is part of the standard library. But that doesn't return us a file descriptor. It returns a file, an stdlib, a standard library file pointer. We can get the file descriptor from the pointer though. We can also unlink the temporary file right away after creating it. We don't have to wait until the end. We can unlink it right away, and it will not be removed from the disk until we call close. So we can actually unlink a file, and it will look like the file is removed, but it's still going to be available. We can still use the file in the application, and then once we close the descriptor, that's when it's actually going to be removed. Conclusion. So thanks for watching this presentation. I'm really happy that you've watched the whole presentation, and I hope you learned something. I think that many people don't know, especially the thing about using file descriptors on the command line. I find that a lot of people don't know that, and for a lot of people that's really a new thing to learn. If you have any questions, that you're free to ask me. If you have any ideas, just let me know. And also, I have a community at SwedishEmbedded.com/community. So if you're managing a team of developers, if you're a developer yourself, if you're a hardware designer, or if you're working on Linux, then just join the community. Go to SwedishEmbedded.com/community. Thanks for watching, and I'll see you later.